Okay, next we look into the use of unit step functions. So up to now we basically discuss two set of categories. One is circuits with sources, and the other one is circuit without sources. So in both cases, so we basically model this first order circuit. So, and for first order circuit we basically discuss without sources case, and then we move to with sources case. So in without sources, what we basically explain, so the impact due to initial conditions. So the capacitor inductor is basically charged to whatever the voltage or current. So then these elements act as a kind of a voltage source or current source in the circuit, and that source basically powered the circuit, and we analyze the circuit where this initial condition of the capacitor or inductor drive the circuit. So in this without sources case, we basically discuss the impact of initial conditions of the capacitor or inductor, and how this initial condition affects to the entire system or the branch voltages or current. So then we found that this entire response, either voltage or current, is basically defined as a natural response of the circuit. So in the natural response, we basically determine the impact of initial condition of this energy storing elements, either capacitor or inductor. So then we move to the circuits where we have external sources also in the circuit. So mainly external DC sources. External DC sources. So our discussion is first limited to a set of DC sources. We have DC voltage source or DC current source in the circuit. So this external source basically pump the energy to drive the circuit. So in that case, in general, so if you have energy storing elements like capacitors and inductors as well in the circuit, so the ultimate response is a sum of these two. Ultimate response is the sum of the natural response and the forced response. So for the forced response is basically comes from the forced term, and this forced term is basically governed by the external sources. So the natural response similarly gives the contribution of the initial condition of the circuit. Initial conditions. So whatever the circuit we discussed in this with sources category, so we have capacitors or inductors in the circuit as well as this external sources also in the circuit. So then this ultimate response is a sum of this natural response and the forced response. So forced response is basically tuned according to the forced term of the differential equation, or the right hand side of the differential equation, first order differential equation. So this force term is basically governed by the sources, external sources you plug into the circuit. So then for force response is basically a contribution of external sources you plug into the circuit. At the same time, the natural response is simply comes from the initial condition, contribution from the initial conditions of the circuit. So then we found that how to evaluate the forced response and natural response. So if you have a kind of a first order differential equation like this, so dxt over dt plus a naught xt plus constant. So we focus our discussions to this DC sources. So then definitely the force term is a constant. So then you have a kind of a first order differential equation having the right hand side non-zero. So for these cases, we know that if your right hand side is a non-zero quantity, we basically have two responses. So this base xt can be written as the sum of the natural response and the forced response. So how to find the forced response? So we take the trial solution for the forced response as a kind of a constant, because so the force term is actually a constant c. So we discussed that if you are proposing a trial solution to the forced response, so that trial solution would basically synchronize or align with the pattern or the function of this force term. So if it is a constant, you can propose a trial solution as a constant. If it is exponential, you have to propose it as an exponential function. If it is a kind of a trigonometric function, you can replace this trial solution with the generic trigonometric function. So likewise, if it is a constant in your force term, so the trial solution for this force response is again a kind of a constant, which is not exactly same as the constant appear in the right hand side of the differential equation. So if this is a kind of a solution for this original differential equation, so this original differential equation should satisfy with that. So then if you substitute this one, so the derivative of this constant k plus a naught k should equals to c. So this is actually 0 because the derivative of the constant is 0. Then from this we can simplify the forced response as c over a naught. So then our forced response is basically xft is basically equals to c over a naught. C is the right hand side of the differential equation and a naught is the zero coefficient of the zeroth order term. So keep in mind this is not a standard formula, so you have to start from the scratch to derive this one. I mean, you cannot simply take this as a kind of a formal equation. So it depends on the equation you basically obtain. So you have to start from the very first equation, proposing a trial solution and substitute it to the original differential equation and find the unknown constant. So then we basically found the forced response of the circuit. So then we move to the natural response. Find the natural response. So how do you find the natural response? Again, we can propose a kind of natural response in this form. So this is the trial natural response for this one. So once you substitute it to this original differential equation, we can get a value for s, or the exponent factor of this one. So we can get this s term without substituting it to the differential equation, and we basically follow a kind of a converting this differential equation to characteristic form. So how do you convert it to the characteristic form? First we have to ignore the effect of external sources, because this natural response is basically driven by the initial condition. So you have to remove the impact of these external sources. So first we need to remove the impact of external sources. So how do you re- uh, remove this impact of this external sources? Is actually let this c to 0. So now your differential equation looks like this. 0. So then we can easily write the characteristic equation from this one. So how do you write the characteristic equation? We can basically replace this nth order derivative with s to the power n. So then this becomes s plus a naught equals 0 and s equals minus a naught. So then we have basically forced response xf t as a c over a naught, and the natural response is like this. So then the total response is the sum of these two, and then substitute initial condition to get a unknown constant. So let's assume like this, at t equals 0, xt equals a naught. So then we can basically so a equals a naught minus c over a naught. So then the ultimate response is a can be replaced with a naught over c over a naught e to the power minus a naught t plus c over a naught. Okay, so this is the ultimate response. So this is the forced response, and this is the natural response. Okay, so then during this last discussion we found that so we have switches in the circuit. So we found that there are two type of modes in the switches. So for this kind of a switch where you have this type kind of a directional arrow, so we basically claim that for t less than 0, so this switch is basically in off state, and t greater than or equal to 0, this switch moves to on state. Similarly, for this kind of arrangement, along with the direction of this arrow, so this t less than 0, we can simply say that the switch was in on state, and t greater than or equal to 0, switch moves to off state. So it means if we basically draw this scenario, so this is something like that. So this is t equals 0. So this is basically off, So this is basically on. Similarly for this one, so it was in on state, and once t comes to 0, this is off. So here, so this is off for t greater than 0, this is on, t less than 0, t greater than 0, t less than 0. So we can simply represent these circuits using this kind of a graphical format. So now our idea is to replace this sage using a unit step function. Unit step function. So UT. So the objective now in our discussion is actually replace this switch, this whatever this mechanical or electromechanical switch, using a mathematical function which is actually unit step function. I believe like you are familiar with this unit step function. So in circuit theories we basically use this notation UT. So this is UT actually, not text, UT. So this is UT. So this basically represent the unit step function. If you define it mathematically, this is 1, 0, t greater than. So if you draw it, it's something like that. So this is our unit step. So t greater than or equal 0, this functional value is 1, otherwise the functional value is 0. So then this is the unit step. So let's assume, what about this one? This is u minus t. This is the mirror image of ut. Okay, so this mirror function of ut is u minus t. So this can be basically defined like this. So t greater than 0, so t less than equal 0. So if you draw it, so it's something like that. So this u minus t, or the time reversal function. So in some textbooks it may refer as time reversal. Function of ut. So you basically take the mirror over this vertical axis. So then you can easily get the mirror function or the time reversal function. Whatever the function, for example, if you have this kind of a function, so the mirror would be, if you take this, rotate out, so this is the mirror. So this is xt, this is x minus t. It's nothing else. So this is ut, unit step function. The time reversal of this ut is simply like that. So we can basically represent this using this kind of a switch. Okay, so then from this, we can basically represent So yeah, so in this case we found that for t less than 0, so this switch is basically was in off state. So then the output is basically 0. So for this one, once it's moved to on state, when this t greater than or equals to 0, so this switch is moved to on state, and we can claim that the states is 1. So initially 0 during this negative part, so then here it's 1 for this positive. So this is also replaced with this kind of a switch. Similarly, t less than 0 less than or equals to 0, so this was in on state, and we claim that the state is 1, t greater than 0, this moves to off state. So it was in 1, and then at t equals 0, this drops to 0. So t equals to 0. So then this, so if you count argue, so these kind of switches can be replaced using this unit step functions. So these kind of switches can be replaced with this unit step functions. So depending on the switching point, now for this example we selected our switching points as t equals 0, so it may not necessarily be at t equals 0. You can basically switch at t equals 1, t equals 2, and so on. So depending on the situation, this unit step function may be shifted to positively or the right hand side or left hand side. Then you can basically get the shifted version. For example, so let's assume your switching is basically happens at t equals 1 second. So if I draw it like this, t equals 1. So then we can simply claim that this can be replaced with the unit step like this. So this switching happens at 1 second. So until 1 second, this switch is open. So until t equals 1 second, switch is open. So then it's turn on. So this is t equals 1. So here it's on, here it's off. Okay. So then we can represent this step using unit step. This is ut minus 1. So then rather having this kind of a switch, you can replace the switch unit step with the shifted version. So this is the shifted version of this original unit step by 1 unit. So likewise, you can adjust your unit step function according to the situation. Okay. So I'll take one example. So I'm referring this exercise 9 in the slide set. So I'm referring exercise 9. So you are given a kind of a circuit having an inductor and a resistor and a kind of a current source. So it's 5 gt. So this is 5 ohm and this is 5 Henry. So first you are asked to draw the current response IGT as 6 ut minus 6 ut minus 1. So how do you draw this one? So we know that, so this is your ut. So this is your ut. So what about ut minus 1 is actually like this. So this is t equals 0. So this unit step is shifted by 1 unit, and this is ut minus 1. Now this is 1. So what about the sum of these two? So during, so let's assume, so t is 0, t equals 1, and so on. Okay. So what about during infinity, minus infinity to t equals 0? So both functions are in 0 state. So this 0 minus 0. So for the time being, we'll draw line. Simplify it like this: ut minus ut minus 1. So now this is ut and ut minus 1. We basically subtract ut minus 1 from ut. So 0 minus 0. So we left it at 0. So then between 0 and 1, ut has a functional value of 1, and this is 1, and this is still at 0. So then 1 minus 0, 1. So from t equals 1, or after t equals 1, t greater than or equals 1, what happens? So ut is a 1, and ut minus also added another 1. So then 1 minus 1 would be 0. 0, 1, 0. So then this is actually ut minus ut minus 1. So with these unit steps, we can basically generate rectangular pulses. Rectangular pulses like this. Or else we can generate staircase type of function. Okay, so you can see a couple of one example in the previous slide. So how do you obtain a kind of a staircase function as a function of unit steps? So it's basically a combination of unit step or shifted version of unit step or scaled up or down versions. So you can basically replace any kind of a rectangular function using unit step and any kind of a staircase type of functions using unit step. So this is a kind of a rectangular pulse or rectangular function. So we basically replace this rectangular function using unit step. So then this 6 times ut minus 6 would be this kind of output. So here t equals 0, here t equals 1, this value is plus 6. So this is basically 6 times ut minus ut minus 1. So this is the current response IGT. Here it's 0, here it's 0 ampere, here it's 6 ampere, here it's 0 ampere. So we have three states, one is 0, the other one is 6 ampere, then we move to 0 ampere. Okay, so then we'll basically try to analyze this system in the next video. Okay.